3.5 is about rational functions. And for rational functions, I'm going to want you to work these out on paper rather than just graph it in the calculator and move on, because you need to know how to actually graph it without the calculator. So our rational functions are p of x over q of x. That is what our rational function will look like. We have domain restrictions, though, because we're saying q of x is some expression there. Our domain restriction is when q of x equals 0. That will be our domain restrictions. So when we have a function like this, we need to find the domain. Those are our x values. We just don't want our denominator to be 0. And anywhere that it could equal 0, we will remove those functions or those values. So we'd say, okay, x equals 0, that's going to be removed. X minus 2 equals 0, that's going to be removed, which means x equals positive 2. And then x plus 5 equals 0 will be removed. So it's x equals negative 5. So the way we write our domain is the set of all x values that are elements of the real number system such that x cannot equal 0, x cannot equal 2, and x cannot equal negative 5. For the next example, we have x over x squared minus 25. We check and see if we can simplify it, which we can do. This x squared minus 25 is the difference of squares. So we can write that as x minus 5 and x plus 5. So then our domain restrictions would be when x minus 5 equals 0 or x plus 5 equals 0. So that'll be x equals 5 and x equals negative 5 when you solve each equation out. So then it's the set. The domain is the set of x values that are all real such that x does not equal negative 5 and x does not equal 5. We're going to use this packet, 3.5 packet, to learn some of these and make sure you understand it. So go ahead and look at problem 1 and problem 1A and 1B. So they've solved 1A for us. So now you're doing, there's solved one and there's a pencil problem. So if we simplify this, factor it, we're able to factor that x squared minus 49. The denominator is x minus 7 and x plus 7. So x minus 7 equals 0, means x equals 7. And x plus 7 equals 0, x equals negative 7. 7, there we go. So it's x all real such that x doesn't equal -7 and x doesn't equal 7.
Is that first one a -7?
Yep. On 1b, can we simplify that denominator? No. So will this ever equal 0? You would subtract 49 on both sides, right? You get x squared equals -49. Can you have a square that equals a negative? No. It'd be imaginary, right? It'd be like 7i. So we don't have any domain restrictions. So when we don't have any domain restrictions, then x is just all real numbers. Okay, let's look at the next part of our notes. In order to graph functions, we've got to be able to look at them coming from the left, coming from the right, and we're going to deal with asymptotes, vertical, horizontal, slant, and sometimes there can be quadratic asymptotes. So we've just got to look at the reciprocal function. This is our parent function of rational functions. Okay, this reciprocal function, y equals 1 over x, if we were to graph it, the easiest way to look at it is by looking at the table. So let's say we do 0. If I plug in 0 for x, I get 1 over 0. What does that mean? Can I do 1 divided by 0? No, so that's undefined. And in your calculator, it'll show error. Okay, what about 1? It'd be 1 over 1. So it'd be 1. So 1, 1. Okay, let's do 2. If I plug in 2 here, I'd have 1 over 2. So it'd be half. So 2 half. And then 3, 1 over 3. Four, be 1 over 4. So it's getting closer and closer to the x-axis. But for it to ever touch, it has to be equal 0. So let's see, what about half? What is half? So I want to see how it behaves up here. Half would be 1 over 1/2. 1 over 1/2, which would be 2, right? Half, 2, like that. Okay, so it kind of goes like that. It's like this. Can it get closer? But we know 0, if x is 0, it's undefined. So it's never actually going to touch that. But what about -1? If I plug in -1 there, 1 over -1 be -1. So -1, -1. And then -2. Would be -1 over 2, or 1 over -2. So -2. And then -3. 1 over 1/3. So it looks like it's following the same path. So it's never going to touch this. So this is an asymptote. This is our y-axis. And it's never going to touch our x-axis either. Hard to see that. So the function looks like this. And it goes on and on forever to infinity. And then it does the same thing over here. So what this means is this is kind of your behavior. As x approaches infinity, so you start on the x-axis, you start at the origin, and as you're going to infinity, the graph, this blue line, is getting closer and closer to 0. So as x, so you start at the origin, as x goes to infinity, so you're going down the x-axis, the line gets closer and closer to 0 without actually touching it. So it's approaching 0. And then as x goes to -infinity, that means you're going to go left. We're going to the left. As x approaches -infinity, the blue line is going to approach 0 on the x-axis. Okay, so let's look at our problems over here. We're going to look at this one. We usually don't look at the soft ones, but we're going to look at this because I think it's important to look at the wording of it. True or false? The notation x arrow a plus means that the values of x are increasing without bound. So this x goes to a plus. That means x approaches a from the positive side. So the positive side is right, which it actually wrote it here, from the positive direction. So from the positive direction, so you're approaching it from the positive direction, which is right. So this is the notion. X approaches A plus means X approaches A from the right. Does not mean it increases with that bound. It means this. So this is definitely false. If it says as X approaches A with the negative sign, what do you think that means? Means the opposite. It approaches it from the negative direction or left. X approaches A from the left. Which is your negative side. Okay, number 2, true or false. If f of x approaches 0 as x goes to infinity, then the graph of f approaches the x-axis to the right. So if f of x approaches 0, so that's your y value. Remember, f of x is your y? So if the y value approaches 0, so that means it's going down, then as x goes to infinity, so it's like this, that's what that is saying, because the f of x is going to 0 and the x is going to infinity. Then the graph f of x approaches the x-axis to the right. It's approaching the x-axis to the right. So this is true. Okay, let's talk about vertical asymptotes. So we are going to look at the denominator. So if we have f of x equals p of x over q of x, in order to find your vertical asymptote, you're going to simplify that, and then you're going to find any zeros. Basically, you're looking at the denominator. So simplify, then set q of x equal to 0 and solve. And those will be your vertical asymptotes. So an example would be f of x, x over x squared minus 9. So we are doing a lot like what we did with our domain, where we're finding what doesn't exist as part of the x values. But in this case, we're finding out, well, where it doesn't exist, is that an asymptote? And so we go ahead and simplify this. We have to factor too. So x over x minus 3, x plus 3. And there's nothing to cross out. So then we set this equal to 0. So I say x minus 3 equals 0 and x plus 3 equals 0. And I solve those. So x equals positive 3 and x equals negative 3. And these are my vertical asymptotes. So the way that we graph those, go ahead and draw your x and y axis. And we're going to draw those as dotted lines. vertical asymptotes at x equals -3. So this is at -3. So we're going to do a dotted line. And at +3 is the other vertical asymptote. So when you graph it, the graphs will approach this in some way, but never actually cross the dotted line. Okay, another example, g of x equals x plus 3 over x squared minus 9. So we'd want to factor it, that denominator. And for domain restrictions, we'll still have that 3 and -3 do not exist as far as x values. But as far as the vertical asymptote, we need to we need to do this first and then find our vertical asymptote. So x minus 3 equals 0, x equals 3 is our vertical asymptote. I'm just going to put VA. So whenever you graph it, you'll only have a vertical line at the 3. Okay, let's go to horizontal asymptotes now. Okay, for horizontal asymptotes, you're going to look at the degree of P of x and Q of x and compare them. And how they compare tells us what kind of asymptote, or where that horizontal asymptote is, or if it even has one. If P of x and Q of x have the same degree, then divide the leading coefficients. And you'll do P of x on top of Q of x. So I feel like we need an example of that. So let's say f of x equals 8x squared plus 2x minus 1 over 4x squared minus 1. These are the same degree. Of 2. So we just divide our coefficients. to get our vertical asymptote. So we say y equals 8/4. Those are your leading coefficients. And 8 divided by 4 is 2. So y equals 2 is our horizontal asymptote. So when we graph it, we're going to have a horizontal asymptote at y equals 2. So it'll never touch this line or cross it. And in this one, you'll also have a vertical asymptote. And so we'd have to find that, but we're not going to find that right now. Okay, so this was if they were the same degree. And then the next one, if P of X has a lower degree than Q of X, then the HA, horizontal asymptote, is y equals 0. So P of X is the lower degree. So the example is f of x equals 4x plus 4 over 6x squared minus 5. So our P of X is our numerator. P of X has a smaller degree than Q of X. This degree is of 1. So if that happens, then y equals 0 is our horizontal asymptote. Okay, so the last case is if P of X has a larger degree than Q of X, then there is no horizontal asymptote. You will need to find a slant asymptote. So P of X is larger, no HA, but there will be a slant asymptote. So let's talk about what a slant asymptote is. If P of X has one greater degree then Q of X, there will be a slant asymptote. Use division to find it. So slant asymptote is when it's one greater. Two or more would be a quadratic asymptote, and we're not covering that in college algebra. It is in pre-cal, but not in college algebra. So we'll do the example f of x equals x squared plus 1 over x minus 1. So the p of x has 1 greater than the q of x. That's a 2 and that's 1. So we are going to divide. So this is actually could be written as x squared plus 0x plus 1. So for division, I got to be able to write those missing terms if there isn't a particular variable in there or exponent. So we'll have x squared plus 0x plus 1. We're going to divide that by x minus 1. So x minus 1 into this. So we're going to do x into x squared, which would just be x. And I'm going to put it over the same degree. And now I'm going to multiply x times x squared. X times a negative 1, negative 1x. And then subtract. When you subtract, you change both signs. Okay, and then so this is actually 1x plus 1. And then x into 1x plus 1. And then 1 times your x minus 1 is x minus 1. Subtract it. So we get a remainder of 2. So we're going to rewrite this as equals. When we divided it, we got x plus 1. And then we did plus the remainder over x minus 1, what we divided by. So to find our slant asymptote, it is your equation that we get when we divide. Equation found from dividing. And also you're going to drop, so equation found from dividing and dropping the remainder. So this is the remainder. This is your equation. So y equals x plus 1 is your slant asymptote, SA. So tomorrow, all we'll need to do is just graph. We're going to graph number 6 in our notes, 6 and 7. before y'all do the assignment tomorrow.